on 567 AM.
And it's that time, Friday, and it does mean we welcome the Naked Scientist. Dr. Chris Smith is back, and he's here to answer your questions. Welcome, Chris. Great to have you back.
Hello, Clarence. Good to talk to you.
Yeah, Chris, are we going to just dive straight into the questions? You
I, I
ready
think we
for
I
it?
think we should. I mean, the only thing that caught my eye today, actually, I was going to raise this because it's sort of you see something like this, and then you think, well, actually, my friends across the African continent will probably be quite pleased to hear this. The National Health Service in the UK has today approved a gene editing platform for treating sickle cell anemia. So basically, what we can now do, or what's been approved for use, is in people who have sickle cell disease, it'll be possible to take blood stem cells, to gene edit them to remove the change that causes the hemoglobin in the cells to go into the sickle shape, which is what causes the disease. And it's one single genetic spelling mistake in those cells. And if you fix that one single genetic spelling mistake, you give them normal hemoglobin. And so what they'll be able to do is to put the stem cells that have been fixed by gene editing them in a dish back into the body and restore healthy hemoglobin to people who previously would have been condemned to having these regular problems with extreme pain, anemia, and many other health problems downstream of that. So I thought that would be a nice sort of good news story we could just pass on today, that major health providers are now taking this sort of thing very seriously, and there is a tool, a genetic editing tool, that can fix it.
Wow. And is it of special significance for the African continent, Doc?
Well, it is because the genetic change that causes sickle cell disease is extremely common in people of African extraction. And you might say,
Okay.
well, why is a disease which can be extremely health harmful so common in a population? And the answer is that it's what's called a balanced polymorphism. It confers a really strong advantage against malaria. If you are a carrier of the disease, it means that only a fraction of your hemoglobin is affected because one of your genes is healthy, not affected, and one is affected, which means about half your hemoglobin is affected. That's not enough to produce severe disease, but what it does do is make your red blood cells completely inhospitable for the malaria parasite. So people who carry the condition are ironically protected from another disease. So this has kept that gene that causes sickle cell disease in higher circulating frequency than otherwise would occur, because normally if you have something which is health harmful, evolution would slowly weed it out. But the pressure of malaria has kept this gene in high circulation in populations in the African continent where malaria is very common. So as a result, you see an overrepresentation of that particular gene. And this means when people then move away from where there is no malaria threat, they nevertheless take that genetic legacy with them. They continue to find sickle cell disease problematic, but they're not receiving any benefit in being protected from malaria. So at the end of the day, it's a health disbenefit for them. And so if we can fix that, and obviously we're not talking about fixing this in the germ line, you're not talking about fixing sperm and eggs. So this is not a change that would be passed on to any children, but you would fix it for that person.
Wonderful news. Let's go to the questions. Keith has a question. Dr. Smith, how does a sunflower follow the sun? Is it only the flower, or is it the stem? Is it the plant that does it?
Yeah, it does track the sun, and the way it does it is that there are sun responsive cells which are all over the flower and the top part of the stem, the neck. And in response to sunlight or absence of light, the production of different growth hormones is tweaked, and it makes the plant grow more on one side than the other. And this has the effect of exerting a torque or a twist on the stem, and that twists the head of the flower round a bit like a radar dish. And this is to keep it pointing at the sunshine, to provide warmth and light for the maturation of the flower head, and also so things that can see bright things like pollinating insects will come in and pollinate the flower. And sunflowers are really interesting because they also use body clocks. They have clocks which are running in the cells in their flowers, and these clocks track daytime, and they use the time of day to trigger the flowering of the flower. Because you look at a sunflower and you think the flower is those yellow petals around the outside. Those are just part of the flower. Most of the flower is the black bit in the middle, believe it or not, because each of those is a little flower in its own right, which when pollinated turns into a seed, a sunflower seed. But you don't want all of them flowering at exactly the same time, because then only some would get pollinated and others would be missed. So the plant actually has a system. So the ones in the middle are pollinated first, they flower first, and then the ones towards the outside come on stream later. And it is operated in a spiral pattern going from the middle outwards, so that insects walk in from the outside and pollinate the ones in the middle, dropping some pollen on the outside as they go. And that way you get a coordinated pollination which is efficient, and it makes sure that all the flowers are able to turn into seeds. Isn't nature amazing?
Absolutely. Donna's got a question for you, Dr. Chris Smith, the Naked Scientist. Your questions, voice notes, text notes. Don wants to know, how does the body determine whether bowel pressure is just wind, i.e. a fart, or something more solid?
Yeah, well, this is the important distinction between a fart and a shart, which is a fart with some solid components. And it's an important distinction to make. And there are a number of what are called anal cushions, which are these bodies which are around the sphincter, and they have innervation, a nerve supply, which enables them to apply just the right amount of pressure to keep the sphincter closed, but to allow through things that you want to allow through without letting solid material through. And it's a very finely tuned, balanced, coordinated mechanism. And if you have a problem downstairs, or you have to have surgery, for instance, hemorrhoids or something like that, or worse, it can disrupt that reflex. And the ability to discriminate between a volume of gas and something a bit bigger is impaired, and this can lead to difficulty, and you end up with a situation where you feel like you can trust a fart and sometimes shouldn't.
We've got a question in from Jabu. It's a voice note in. Let's take a listen.
Good morning. When I'm sleeping during the mosquito season with my partner, the mosquitoes munch at me a lot, more than they do to her. So I am perplexed as to what is actually happening. What makes them to bite me more and never to bite her at all? Thank you.
You are so right. And there are so many people who are listening to this saying, that's me. And there are equal numbers of people who are saying, and the wife is me. Some people are natural mosquito magnets. Other people are repugnant to mosquitoes. And people have done quite a lot of research on this now, because malaria and other diseases spread by mosquitoes makes mosquitoes the most dangerous animal on Earth. They are responsible for more disease and more loss of life than any other creature on Earth. So we want to get to the bottom of it. And the answer is that mosquitoes are attracted by a number of different cues or stimuli that tell them where we are. And it's actually the female mosquitoes that go after us, because at certain times of the year when they're breeding, the production of baby mosquitoes, in other words eggs, requires a lot of protein. So the mosquitoes need a high protein diet in order to keep up their egg production. And the females specifically. So they will, at certain times of the year when they're breeding, track down sources of a blood meal. That often, because the kinds of mosquitoes that carry malaria, means us. And so they'll come looking for an animal they can latch onto and feed from. They use a number of different stimuli. One is temperature. They can tell where it's hot and it's cold. They like their food hot. No point in drinking cold blood. So they'll find a warm source, because a warm source is probably a living source and that's got blood. Second, they have an acute sense of smell. They don't have a nose like we do. They have antennae off of their head, which are covered in fine sprays of nerve endings, which are themselves covered in chemical receptors. These are like docking stations for molecules. These are directly wired up to the insect's nervous system, enabling it to track down the source of a smell. And because it's got two antennae, it can resolve between one and the other a change in concentration. So the mosquitoes fly backwards and forwards across the room, and they can effectively sniff out where a smell is coming from. And they do this for carbon dioxide, which is the gas we breathe out when we're just going about our business. But we also produce a host of other volatile chemicals, both on our breath but also through our skin, which gives us our unique odour. Some of those chemicals mosquitoes love, some of them they absolutely hate. And some people, by chance, produce more of some of the ones the mosquitoes love than the ones they hate, and so they are more attractive to mosquitoes. Other people produce relatively less, so they're less attractive to mosquitoes. And in some circumstances, you'll have two people side by side. One smells better to a mosquito, so given the choice, they'll go for the one that they prefer the smell of, and they'll feed from them. So you get more bites than your wife. Isn't she lucky?
Then a question about intelligence and the relativity of it all. Why is your intelligence different to mine? Why are you a doctor and I never will be able to be one? And the question goes further from Krista. Why are humans the only species with advanced intelligence?
Well, I think it depends how you define intelligence, Krista, to be perfectly honest. We think that about half of what we call intelligence is genetic. That's our nature. It's the genetic hand we're handed by our parents. And we know that genes do play a massive role in both in humans but other animals, how our brains form, wire up, and their propensity to be able to take on new information, process it, assimilate it, and then respond meaningfully to it. So half of the time, what we're destined to do and achieve in life is written into our DNA, and that's therefore written into the way our brain wires itself up. But half is still a lot, which means that the environment, nurture, plays a huge role as well. So you can have someone with a wonderful genetic hand to play, but if they're not given the opportunity, if they're not given the chances, if they're not given the opportunity to develop that potential, they'll never reach it. So a good teacher is probably one of the most important things we can do for anybody in their life. Education is one of the most valuable things you can do for anybody, and you only have a limited time to do it because the brain is at its most moldable, it's most plastic when we're small, and the older we get, the harder it is to learn new stuff. And that is a scientific neurobiological fact, unfortunately. So basically, humans are not the only highly intelligent species, because you could say, well, an animal that knows, in inverted commas, how to find its way from one side of the planet to the other, the Arctic tern, flies around the world many times and does it unerringly without getting lost. I'd say that's pretty intelligent. There are other animals that can find their way across environments that would kill some species in minutes, and they are absolutely fine doing that. I'd call that intelligence. So it really comes down to what your definition of intelligence is, but we think, again, about half of that is genetic, certainly in humans, and the other half is the environment that we grow up in.
So is human intelligence different to intelligence in animals? And Lance wants to know about an octopus. How intelligent is an octopus?
Well, Lance, we think that the family of octopuses that we study are pretty intelligent, actually. They seem to be able to have quite good problem-solving abilities. And we, for many years, thought that we were kingpin as humans, and we had these enormous brains, and we were top of the pile. But it's as we've looked at other animals, we've realised that in fact there are many animals that have incredible reasoning abilities. My friend Nikki Clayton at the University of Cambridge studies this sort of thing, and she's getting interested in animals like cuttlefish, but hitherto she's been very interested in studying members of the crow family. She calls these birds feathered Einsteins because they have the ability to reason their way through problems that even 3- and 4-year-old children can't solve. It's worth bearing in mind that most people can't tie their own shoelaces until they're about 5 or 6 years old. Most kids can't work out how to do the puzzle that Aesop wrote about, where you drop stones into a bowl of water to raise the water level to get something off the top of the water. Most kids can't work that out until they're 4 or 5 years old. Nikki Clayton's birds are doing it, and they're not even 1. So, in other words, animals are very intelligent, but they don't have to have a massive brain like we do. And this is because their brains might be slightly differently structured. They may have smaller nerve cells, therefore a high density of nerve cells, and they may be configured to learn in a variety of ways. And we think that animals like the cuttlefish and the octopus, Nikki's now looking at cuttlefish, they also have an incredible propensity to solve problems. And people have got some footage. David Attenborough has, in some of his documentaries, shown wonderful footage of an octopus either hiding itself in a cunning way or using its tentacles in a clever manipulative way to access food that you wouldn't think was immediately intuitive. So I think these animals are quite, inverted commas, intelligent.
Okay, we got a voice note in. I think it's from Jolene. Let's take a listen.
Can you please explain to me what the cause is of this like a zigzag light that comes in at the side of my eyes? Sometimes it's on the left side, sometimes on the right side. It comes from a distance and it comes closer and closer to my eye. Someone told me it could be a migraine, but I don't know what it is.
Thank you,
Does
Marjo.
sound like migraine. There are two sorts of migraine. There's the migraine happening in your brain, and there's a migraine happening in your retina, which is the patch of light-sensitive tissue at the back of the eye. Now, they're actually two different things. And a retinal migraine is where you'll usually get a patch of light, a zigzaggy line, which will move in from the periphery, go across the centre of your vision, making it very hard to see. When you look at things, you can't read the print on a page, for example, and then it will migrate back out of the middle away towards the periphery of the eye and disappear. And usually you're absolutely fine in the aftermath. And there's usually no headache, nothing like that. And it's thought to be a wave of abnormal electrical activity spreading across the retina, which disrupts vision temporarily because the electrical activity is disrupting the way that the photoreceptors, the rods and cones, talk to the nerve cells that then transmit signals to the brain. So you get barrages of abnormal visual information being sent to your brain. But it doesn't have any kind of pain or other connotations. And we don't think this is health harmful. It happens spontaneously in some people. It also only happens in one eye at a time. You don't get this happening on both sides of the world. And this is the giveaway, how you distinguish between a retinal migraine, like I've just described, and a brain migraine. Because if you have a brain migraine, both of your eyes will be affected, and it will affect one side of the visual world. Because when you're looking at something, everything on the right-hand side of your body is actually being processed by the left-hand side of your brain. And everything on the left-hand side of you, when you look to the left, even though that's putting input into both eyes, it's being presented to your consciousness by the right side of your brain. And when you have a migraine, this is a neurovascular problem where abnormal electrical discharges in the brain have caused initially a constriction of blood vessels in a certain territory of the brain, and then later those blood vessels dilate painfully and it causes this thumping headache. And the giveaway this is going to happen is you get that visual disturbance on one side of the visual world, which tells you it's happening on one side of your brain only. And once that wavy line has gone across in the same way as it did with the retinal migraine, disrupting your vision and so on, then people very often develop the symptoms of a full-blown migraine. They can feel sick, they can feel tired, they can sometimes be sick, and they get a very bad headache. And you're doing the right thing if you're getting the headache and that kind of thing, taking a paracetamol or something, lying down, taking it easy in a dark room and reducing stimulation for as long as it takes the headache to go away. That's the right thing to do. But that's how you distinguish between a retinal migraine, which generally doesn't have major consequences, and a sort of neurological brain migraine, which can have consequences in the aftermath, and sometimes it can cause temporary neurological problems like pain, loss of sensation, tingling, and weakness on the affected body side as well.
A little bit of a heads up from both Peter and Brenda. They want you to watch My Octopus Teacher. It's a local documentary. It was made in False Bay about a local guy's relationship with an octopus. I think it is illuminating. Both of them want you to see it. But let's go to Lisa's question.
Hello, doctor. Thank you so much for that very interesting thing about the animals and like a crow learning about the puzzle. My question is what's the lifespan of a crow? Because I think you can't really say, if a child can do a puzzle by 5 years old, you would rather know like what percentage of their lifespan is that age compared to the crow. Because I don't know how long a crow lives, but let's say, for example, it lives 20 years and a human lives 80 years. Then maybe by the time the crow is 1 year old, it's kind of the equivalent to a 6-year-old child. I don't know, maybe. What do you think?
Thank you for the question. In terms of how long they live, in the right sorts of environments, these animals can live for decades. They're really long-lived. Birds live longer and disproportionately long for their body size than perhaps they should do, but in ideal conditions, that is. In the wild, there are all kinds of pressures on them, which mean they might not live as long. But A decade is not unusual for members of the corvid family. But you're right to highlight the fact that their rate of development is going to be different. You couldn't have an animal that lives in the nest and has to live in a range of different environments taking as long as a human child does to develop. You're absolutely right. So they have to speed up their development. And they're not alone in doing that. Most animals do that. They're either born much better developed and able to cope from the get-go. They're called precocious animals, or they have a very fast rate of development during which their parents have to care for them and look after them in order to protect them, and then they're independent. I've just got a new puppy because my dog became a dad about 3 months ago, and so we've now got this puppy. She's about 10 weeks old now, but the rate of development is absolutely amazing. You think this is a 10-week-old. If you're a 10-week-old baby, it would be just about beginning to smile and laugh at you meaningfully, but it would lay there gurgling on its back completely helpless. This puppy is already learning to sit, stay, leave, and occasionally not bite my feet. So, yes, you're absolutely right that age is important, not to make a direct comparison. But the point that Nikki Clayton's making is it helps us when we think how developed we have to be before we comprehend things like tying up shoelaces, like reasoning through puzzles, such as dropping stones into water. And there's one other amazing experiment they were doing where these crows wanted to get the rubbish out of a bin in a motorway service station car park, and the crows joined forces, both sat on the rim of the bin, reached down and each grabbed hold of a bit of bag, pulled the bag up, clamped it under their other foot to hold it, then reached down and got a bit more bag and lifted it up, and they kept doing that until the rubbish was lifted up in the bin to the top. So then they could all, including their mates who were watching, come and get the rubbish out of the bag without having to go into the bag. I mean, it's just amazing. But because they're precocious animals, they have to develop a bit faster. They do get these amazing abilities. But you have to get quite a complicated human brain before we're able to do equivalent sorts of tasks. That's the point she's making.
Let's squeeze in the last question then. What happens? I guess it is the irresistible force paradox. What happens when an unstoppable force meets an immovable object?
Well, I don't know. I don't think we would know. The answer is that there's presumably a big bang. What's immovable? Nothing's immovable. As Newton told us, nothing moves until a net force acts on it. That's actually his first law. An object remains at a constant velocity until it's acted on by a net force. So there's no such thing as an immovable object, because you'd have something which was moving at a particular velocity, which could include a velocity of 0, and it would then be acted on by a force which would apply, because of Newton's second law, force is mass times acceleration. You would get a force if you accelerated that object. Equivalently, you would, if you applied a force to something, get an acceleration. So it would move, but it might move by a tiny amount you couldn't really measure.
So something's got to give.
Something's got to give. And interestingly, if anyone's now fascinated about the work we've been talking about with big-brained animals and so on, you can look up Nikki Clayton's interview with us. I did a whole half hour with her on this sort of thing. If you look up the Naked Scientist podcast and look for Titans of Science, Nikki Clayton, you can listen to what she has to say. She's absolutely fascinating. She's even doing magic tricks in front of animals. And she's got this lovely discovery that if you do a magic trick that fools a human on an animal that has hands, like monkeys and so on, they are falling for it just like a human does. But if you do it in front of a bird, which has wings, doesn't have hands, the birds see straight through the trick straight away. But if you do magic tricks that have things that involve movements like wings, the birds are then duped. So she thinks part of the way in which we solve and see through illusions and magic tricks is by mapping onto our own body plan what the other person or thing that's doing the illusion is doing.
We're going to have to wrap it there. Again, big thanks to the Naked Scientist, our weekly interaction on Friday. Dr. Chris Smith.
On 567 AM.